Hey guys, this is the Physics 2211, Lab 2, Motion of a Falling Object. Let's get into it. Alright, so the contents, we're going to go over the necessary background knowledge, video and tracking results, the computational model with only gravity, computational model with gravity and drag considered, and the analysis of those three models, the simulation, gravity with drag, and gravity, and then the what if and what does it mean for this week. So, background knowledge, Newton's second law. This is about F net, M8, mass times acceleration equals F net. That's going to determine your acceleration. The net force, of course, is the sum of all the forces on one object, such that there will be either a magnitude that is beyond zero, or the thing's going to be at rest, or at least not accelerating, so meaning either at a constant velocity or at rest. So, gravity and drag. Gravity is the downward force caused by Earth on the mass. Its magnitude is equivalent to the object's mass times g. It's always pointing downwards because in any on-Earth projectile motion, it's always going to be pointing downwards. Drag is the air resistance caused on the object. Its magnitude is equivalent to the drag proportionality coefficient times the velocity squared. All right, simulation. So here's the video. We're up on top. It's about a 2-meter drop, maybe a little bit more. It's about 2.5-ish meters. So we use a cardboard cheese topper. This is going to have a lot of drag. It's a circular object with a little bit of a casing on it, so it's going to cause a lot of air to get under there and create a lot of drag, causing it to be a lot slower of an acceleration than it would be just purely due to gravity. So we did this in 0.1 second time intervals. All right. So here's the first computational model with only gravity. So the net force is going to be equal to gravity, meaning that the acceleration is going to be equal to 9.8. Drag is ignored, and the object has a lot of drag, so this position is going to be a good bit off. You're going to see that it's going to be more off towards the end than it is in the beginning as the velocity increases, because as the velocity increases, the drag is going to increase. So as we see, as we go over here, we look at the positional model on the top. It's a concave model. The speed is increasing, meaning that it's going to be a downward slope down here on the velocity graph. It's going to be, that slope is going to equal to negative 9.8 meters per second, as the derivative of position is your velocity, and the derivative of velocity is your acceleration, equal to the acceleration due to the constant g. So if we go into this code, we're looking at, we made the Fg equal to the mass times the gravity. J hat is pointing directly downwards, so it's just a vector 0, 1, 0. F net equals Fg, because that's all that we're considering. And then we just used our velocity update and our position update formulas. All right, second computational model, we're looking at F net equals F grab plus F drag. So position of the object is significantly more accurate now that drag is included. As we're going to see with the velocity tends to kind of get off at one point where it starts going at a horizontal line. That's going to be your terminal velocity. That's where it's a constant velocity because the drag and the gravity is going to equal. And if they're equal, that means there's no net force. No net force means that it's going to be a constant velocity. All right, so if we look at the code here, we're going to see that we made drag equal to the proportionality constant we got through running different simulations, seeing which one was closer, and that was the easiest way to get B in this situation. And then we multiplied it by the formula we saw on the other slide times velocity squared. And then we added that as our F net using, again, the velocity and position update formulas. All right, so analysis of data. So we got these three lines. The green is our only gravity. As we can see, it got a greater and greater position difference at the end as the acceleration continued and it did not reach terminal velocity. The other line is our gravity plus drag, and it's much closer to our video data. All right, so what if and what does this mean? So which models, if any, predict the terminal velocity? So we're going to see that the one with drag is going to predict the terminal velocity, because terminal velocity is when the drag equals the gravity magnitude. That means that there's going to be no net force in the object, and that is going to be at a constant velocity. As we can see in this velocity graph on our drag model, it levels off at the bottom, meaning constant velocity. Therefore, the net force had to be 0. So, would throwing the object downward affect its terminal velocity? No, because the terminal velocity is based on the speed. It's not really based on what the initial speed is, it's what the speed is at a certain moment. If we look at the same graph, and you can see that at the velocity of 2.4 meters per second is where it went off. It wasn't really a time thing. It wasn't that it was in the air for 0.4 seconds. It was that it, at 2.4 meters per second, that was the squared time that was equal to the gravity at that time. Thank you.